Okay, let's resume the teaching. Now, let's go on this next topic of the domain-specific architecture. So actually, RALU is the rectifier linear unit, and then I don't know how to pronounce it. This abbreviation form of the rectifier linear unit. Okay, so in the neural network functions, these are some representative computation kernel, and then domain-specific architecture processor supports this repeated function of the neural network, like a matrix multiplication. And then it's actually the matrix multiplication is the most important function of the neural network. So the DSA processors support this matrix multiplication computation. And then let's see the example of the domain-specific architecture. And then actually these domain-specific architecture processors are called the accelerator. And then as we can see, these domain-specific architectures accelerate the computation of the neural network. Because neural network is very popular recently, and then many people requires some high performance for the neural network applications in the server architecture. And then let's see the Google TPU. The TPU is the TensorFlow processing unit as TPU, and then it is developed by Google as a software company. But as you can see, Google also developed their own hardware. Actually, Google actively developed this domain-specific architecture processor, accelerator, and then server system. Also, Google is developing their own storage, actually smart storage, like a storage system. That's interesting. Google is working for hardware and then computer system. So that's why the computer system and the computer architecture is very important, because it is tightly related to the performance of the computer system, and then many aspects of our server system, and then some cloud infrastructure, and then many aspects of the computer system hardware. Okay. So this is the board photo of the Google Tensor Processing Unit. And then it's actually this is the ASIC. So it's an ASIC. So this is the TPU chip, and then you can find many memory chip around this TPU chip. So this is the DDR3 memory, and then this TPU board is connected to the server system via PCI bus. So actually this is the coprocessor, and then is similar to the GPU. Also, GPU is connected to the host server system via PCIe bus. So the GPUs are also coprocessors, and then TPUs are also coprocessors for neural network applications. And then this TPU support the 256 by 256 8-bit matrix multiplication. So actually this TPU is a domain-specific architecture just to accelerate the computation of matrix multiplication. Also, TPU includes the large scratch pad memory. It's the buffer for the weight value, and then some data input, and then so this and TPU also has the very large size of scratch pad memory. And then this slide shows the architecture of TPU. So as you can see, TPU is connected to the host system via PCI bus. So there is the PCI interface here, and then this is the off-chip I/O, off-chip interface, input and I/O, output interface. Also, as you can see, TPU has the TPU TPU board has the DDR3 memory chips, and then these DDR3 DRAM chips are connected to the TPU. So there is the DDR memory controller inside of the TPU GPU chip. Oh, and then also TPU has the host interface module, and then this host interface module is connected to the PCIe interface. So these are the, also as I said, TPU has the large unified buffer. This is the on-chip scratch pad memory, and then also the data is read from this DDR memory, and there is the weight FIFO is here, and then this weight values are stored in this weight FIFO. FIFO or FIFO is so some people said it as a FIFO or FIFO. And then, as you can see, there is the matrix multiplication unit is here, and then the weight values are value comes from the weight 5 people, and then some data comes from this unified buffer here, and then the accumulator, and then activation, and then some computation unit is here. So these are some control part of the TPU. So actually this figure is copied from the TPU paper, and the TPU paper was presented in ISCA 2017, and I was there. And so TPU also support the instruction sets. So actually these instruction sets are very simple compared to the general purpose instruction set architecture. And there are 5 different instructions for TPU, and then for most of the instructions are data transfer instructions, like read host memory and then read weight, like also matrix multiplication or convolution instruction. So actually these instructions execute the matrix multiplication. Actually the TPU is the TPU just to support this large bunch of matrix multiplication, and then that's it. And then for this matrix multiplication, TPU needs to receive data from the host memory. So this data is transferred from the host memory. So and then the data is also read from the on-chip memory of the main memory of the TPU board, equipped on the TPU board, and then so these instructions are supported for the data read. Also is a matrix multiplication, and then activation, and then write to the host memory. So these instructions are very simple. So I said that in the previously I said that there are some design approaches of the DSA, and then you can say that to minimize the data movement. So actually data movement is very deterministic because this TPU is designed for the neural network operation. And then basically this neural network operation is the matrix multiplication between the input data and weight data. So TPU also supports some deterministic data movement, and then like read host memory and then read weight. So very simple. And then the final result is transferred to the host memory. The TPU also supports this write host memory instruction. So these are the data movement instructions. So it's very based on this guideline. TPU is also has very simple and deterministic data movement instructions. Also invest resources into more arithmetic unit and bigger memories. And then we will check about this factor on the TPU, and but it is true that TPU has the very large size of matrix multiplication engine. Parallelism is okay because it's some TPU has the dedicated hardware for matrix multiplication, and then the data size is also fixed as a bit. So this is the main computation engine of the TPU, matrix multiplication. So this is the some flow. This figure shows the flow plan of the TPU chip, and then as you can see, the dedicated buffer, so unified buffer, occupies the 29% of entire chip area, and the matrix multiplication is the computation unit, occupies the 24%. So this unified buffer and the dedicated memory and computation unit occupies the more than 50% of the entire chip area. And so TPU also requires the DDR interface, the two DDR interfaces, and then PCI interface is here. And then also accumulator is the also computation unit. It occupies 66%. So you can find some other miscellaneous part of the TPU. But as you can see, TPU is very simple. Actually, the structure of TPU is very simple. And then this simple architecture is good for power consumption and energy efficiency of the TPU. Also, TPU supports the matrix multiplication, and then actually the TPU supports the systolic array computation. And then this figure shows the some data flow of the systolic array computation. So these are the input data, and then these are the computed weight matrix. So firstly, the matrix x1 is multiplied by the weight 11, and then this partial result is computed, and then both of this computation multiplication with the weight 12 1 2, and then this input data x2, and then the computation result of this weight 1 1 and the x1 is used for the computation for this matrix multiplication. And then this data is transferred to the weight 2 1, and then also computed with the weight 2 1, and then this partial result, okay, computed result is also transferred to the neighbor, and then is computed with the matrix x3. So for the systolic array computation, the weight actually the input data is input data comes from the top to bottom, and then some partial result of this from with the weight values are computed and then transferred to the right. So move to the right, and then it's accumulated, and the entire values computation matrix multiplication partial result are accumulated like here. So TPU hardware also support these data computation and data movement efficiently, and then you can, so data is moved here, right here, and then partial sums are moved to the top to bottom. So it's a partial result, the direction of the partial result, and then this is the direction of the partial result, and these are the direction of the data. So it's a data for the TPU matrix multiplication, and then weight is here. So TPU's hardware architecture efficiently supports this systolic array computation, and then this computation is frequently observed in the neural network application. So TPUs are hardware unit, or the computation unit is designed for efficient matrix multiplication and accumulation, because these operations are frequently found in the neural network applications. So actually the structure is very simple. If we compare the structure and architecture of the TPU with the out of the processor, and then you can think that, oh, TPU architecture or TPU structure is very simple, right? But as you know, the simple architecture is very beneficial for the energy efficiency and the power consumption. Also performance. The domain-specific architecture has invested some large amount of resources for the computation unit. TPU is also true, but the TPU for the computation, the TPU actually more than 30% of area is invested for the computation unit. So the performance is also good. Actually, for the general purpose processing, this matrix let's think about the matrix multiplication. Actually, we know that the GPU architecture is very good for the matrix, this parallel processing, but for the CPU, the data is repeatedly fetched from the data cache and then the lower level cache, because the data size may be very large, and then this large size of the data cannot fit in the this small data cache. So problem is that the cache is repeatedly thrashed, and then so the data is evicted from the cache memory. So the data is refetched from the lower level cache or some the last level cache, and this is the very significant performance degradation factor. But the TPU has the large size of on-chip scratch pad memory. So this large size of matrix elements can be stored in this on-chip buffer, and then this data can be efficiently computed by this computing unit of the TPU. And then also as TPU paper, the Google also compares the efficiency and then some power consumption metric of the TPU with the other general purpose processors, and then actually multi-core processors and then GPUs. So if you see this performance power consumption metric, the TDP is actually this processor is the Intel multi-core. Haswell is the Intel multi-core Xeon processor, and then NVIDIA K80 is the NVIDIA GPU, and then it's TPU. And then is the size of the chip, and then I don't know. And then you can find the clock frequency of the Intel CPU, GPU, and then TPU. And then let's see the clock frequency. GPU clock frequency is the lowest, and then Intel clock frequency is the highest. And then let's see the TDP is some designed power consumption, and so as you can see, the TPU consumes the lower power. Then this is some operation, the performance. Then you can see that the performance of TPU is very high compared to the Intel CPU. And then as I explained, TPU supports the 8-bit matrix multiplication. So this is the operations for 8-bit data. And then on-chip memory is different. And then so it's a DRAM size. It's a host memory size. And then this is the host memory plus GPU memory, and then so host memory plus TPU memory. And if you see that is a TDP for Intel over 500 watt, and if you use the GPU, it's the over 1800 watt. Why? So it's so high. So actually the GPU consumes much power. And let's see the TPU. So power consumption is larger than the Intel CPU, because this is the CPU plus 4 TPUs. Okay, so actually TDP is larger than the Intel CPU, but what's the performance? Performance is very high compared to the general purpose multi-core CPUs. Okay. Also, Google also shows the performance per watt is the performance divided by power consumption. So because the power consumption of the TPU server system is higher than the Intel server system. So this is the performance per watt, and then the blue graph compares the GPU performance, GPU over CPU, and then this red TPU over CPU, and then yellow TPU over GPU, and then the green is the TPU dash by CPU. This is the enhanced version of TPU, and then this is also enhanced version of TPU over GPU. So it's the total performance per watt, the incremental performance. So you can see some more advanced performance per watt of TPU in this graph. So if we compare the GPU and CPU, this is just several. It's a 1.2 or 2.1, 1.7, 2.9. But if the TPU is compared with the CPU, it's a 17, the 10s, like 41 and 83 millibars. And then compare with the advanced version of TPU, is up to nearly 200. It's very amazing. And then CPU, and then compare with the GPU, it's like 68. So this graph shows that the efficiency or performance per power is the important metric in the server system, because the power is the cost of the system, and then performance is just the performance. So this metric shows the invested cost, the performance output over the invested cost. So as you can see, TPU is the most efficient solution for a neural network, right? Like TPU, enhanced TPU over GPU is the over 68. It's up to nearly 70. Okay, so this graph shows that the TPU performance is better than the GPU. But when the Google presented this result during the ISCA 2017, the Bill Darley is the actually NVIDIA the scientist, NVIDIA scientist and the MIT professor. So he said, so if the TPU is compared with some modern GPU, so then this metric will be lower. So actually in this paper, the performance of a TPU is compared with some old generation of GPU, NVIDIA GPU, but GPU is also advanced, so the performance is improved, and then the power efficiency is also improved. So he argued that in this paper, the performance of a TPU is compared with the old generation of the GPU. So that he said that it's not fair. but but so actually the TPU is has the dedicated hardware for the matrix multiplication. So I think that with this dedicated hardware and then proper structure, the TPU is more efficient than the GPU for the neural network processor. So the recently the NVIDIA GPU has the Tensor Core. Actually, Tensor Core is just the Mac engine. It's a multiply and accumulator engine. It's the Tensor Core over GPU. The recent the modern GPU architecture has this Tensor cores. So the modern GPU architecture is good for the machine learning or neural network applications. So what is the advantage of a TPU? It's the performance and then also power efficiency. The performance per watt is the also important metric for the server processors. And then it is because the TPU has the dedicated hardware and dedicated memory. That's why domain-specific architecture is efficient for the specific application of a specific domain. But what is the disadvantage of domain-specific architecture? So I think there are two disadvantages. The first disadvantage of domain-specific architecture is that it's programmability, program support. Actually, for the general purpose application, like general purpose processor, we have the many we have the good support of the community for the compiler or operating system for the this general purpose processor like a CPU or even GPU. A GPU development environment is supported by the NVIDIA, strongly supported by the NVIDIA. But for the domain-specific architecture, it's some specific hardware for some specific domain of application. So it's not easy to find some development environment. Also, it's not easy to find some appropriate application for this domain-specific architecture. Also, the second disadvantage is that it's just domain-specific. So this actually the TPU cannot run the other types of application. Also, the efficiency is maybe very low. So as I show you, the TPU only has TPU supports only a few instructions like data movement or data computation, and the number of instructions is very small compared to the general purpose processors, and that is also another disadvantage of domain-specific architecture. And then let's see another example of DSA, Microsoft Catapult. So actually, Catapult is the FPGA-based domain-specific architecture processor, and then this Catapult is equipped on the server system. Actually, the Catapult is connected to the some network of this server system. So this Catapult board receives the data from the on CPU, and then also compute the some instruction with some FPGA of the Catapult board, and then deliver the final result to the other CPU. This is the some structure topology of the Catapult, and then you can find the detailed topology and then how the topology of the Catapult in the paper. So this Catapult is also presented in the ISCA conference, I believe it's SCA. Okay, but the Catapult is just a FPGA based domain specific architecture. So this is the architecture of the Catapult, and then some photo of the Catapult board, and then how the Catapult board is equipped in the server system. So actually the structure of the Catapult is very simple. It's a FPGA chip is here, and then the 8 GB ECC DRAM is connected to the FPGA, and then the JTAG, and then flash memory is also attached to the FPGA board. So this is the FPGA chip, Catapult FPGA chip, and then these are the memory, DDR with the ACC, and then some flash memory, and then JTAG is connected to this Catapult board. So as you can see, the Catapult board is very small, and then this Catapult board is connected to some network interface of the server system. This is the server. You can find the HDD here, CPU is here, and then DRAM DIMMs are here, and then this is the Catapult board. Oh, so this is the architecture of the Catapult. Actually, the Catapult is the FPGA. What is the FPGA? FPGA is the field program FPGA. Field programmable gate array. So in the FPGA, we can implement any design with the RTL. It's like a Verilog or VHDL hardware description language. So this is just some FPGAs here, and then inside of FPGA there are some peripherals, and then these peripherals are the hardwired IP, and so these hardwired IPs are equipped, fabricated in the FPGA chip. So this is, as you can see, this Catapult chip has the host CPU interface, and then also Catapult is connected to the host via PCIe bus. Okay. Also, Catapult is connected to the network of the server system. So this network fabric is also connected to the Catapult FPGA. Also, other peripherals IPs are equipped in the Catapult FPGA. So with this Catapult, then actually the many different accelerator can be implemented on the Catapult board, because the Catapult board is just FPGA. So actually we can implement any hardware inside of the FPGA. This is the field programmable gate array. It's a programmable gate array, so we can implement any hardware. But what is the issue of the FPGA? The performance of FPGA is lower than the ASIC. Also, the power FPGA will consume more power than FPGA is not power efficient compared to the ASIC. But what is the advantage of FPGA? It's programmable, so we can modify the hardware inside of FPGA if required. So this is some example of the convolutional neural network accelerator implemented on the Catapult. And then, as you can see, this structure of the CNN accelerator is very similar to the Google TPU, because what's the CNN? CNN is composed of a matrix multiplication. So CNN accelerator just implement the matrix multiplication hardware. So this is the processing engine for the matrix multiplication, or some CNN matrix multiplication. And as you can see, this is the weight input. This is the input data for the matrix multiplication. And then this architecture shows the processing element, of the CNN accelerator, and then you can see that this weight buffer is here, and then you can find the buffer for the input data, and then it's a functional unit. What is the functional unit? It's a multiplication of the element between input data and the weight, and then you can find some additional functions, and then function units here. Okay. So this architecture of the CNN accelerator implemented on the Catapult board is similar to the Google TPU, because this accelerator also performs some basic kernel. It's a basic computation kernel of the neural network. Is the matrix multiplication and accumulate actually the matrix multiplication. So this Catapult is also exploit to accelerate this matrix multiplication. Okay. So IntelliCrest. So actually IntelliCrest is developed by the Nirvana. It's the it's a machine learning accelerator chip maker. And then this IntelliCrest is the accelerator for neural network training. And then this slide shows the architecture of the IntelliCrest. It's a training accelerator. So IntelliCrest is connected to the host system via PCI generation 4. So this is the PCI interface. And then via this PCI bus, this Crest is connected to the host system. Also, in order to support the high bandwidth, the IntelliCrest has the 4 HBM2 memory module, and there is the memory controller here. There are 4 memory controllers. Then 64 range of SerDes. SerDes is a serial and deserialized link. And then there are 24 tensor processors. So as you can see, this is a tensor processor. So this tensor processor accelerates the TensorFlow operation. Okay. So these are the tensor processor core here. So you can find 24 tensor processor cores here. And then this is the HBM controllers. And then you can find the PCI interface here. Okay, and then this figure shows the inside of the TensorFlow tensor processor core. As you can see, the tensor processor core has the MAC array. It's a 32 by 32 MAC array. It's a multiply and accumulate array. Because also it has the convolution engine, and then it has the some dedicated memory. It's a buffer memory is here, and then these TensorFlow cores are connected to each other with the interconnection network, and then this is the interconnection network router here. I think this tensor processor cores has the mesh type interconnection network, because it's very similar to it. So this structure of this router is similar to that of mesh network. Okay, very interesting. So these are some basic unit of the tensor processor core, and then IntelliCrest has the 24 tensor processor cores, and then these tensor processor cores are connected to each other via mesh type interconnection network. Okay. So it's just a compute cores for matrix multiplication, MAC, connected each other. So interesting. And then FPGA accelerator. So the FPGA accelerator has some card type accelerator equipped on the server system, and then this is some one FPGA accelerator card, and then this accelerator card has actually FPGA chip connected to some memory like HBM or DDR memory, and then this is just FPGA, and then this FPGA card is connected to the host system via PCI bus. So there is the PCI interface. So this is some basic structure of the FPGA accelerator, and as you can see, these 8 FPGA accelerator cards are equipped under this server system. So what is the benefit of FPGA accelerator? It's the programmability, that we can implement any hardware unit on the FPGA. So like some other domain-specific architecture processor, some similar hardware is implemented under this FPGA board, and then also the data is fetched to the memory of this accelerator board, and then the FPGA will fetch the data, and then performs some basic computation of the for the neural network, some other domains of application. So advantage: programmability, but also for this domain specific architecture, so we need some program so this programmability is different. This programmability means that it's the programmability for RTL, it's a hardware description language, and then also for this challenge for this FPGA based accelerator means that we need some programs language for accelerators. So actually Intel or Xilinx is actually, Intel is the Altera, and then Xilinx. So there are two big companies for FPGA, Intel and Xilinx, and then these manufacturers use the OpenCL for for programming for programming the code that runs on this FPGA type accelerator. So in order to write the OpenCL code, we need to understand the hardware inside of the FPGA this chip. So actually it's not easy. The learning curve is so steep. So we need to understand the OpenCL. So this is some disadvantage of the FPGA based accelerator. So recently the Xilinx or Intel provide the API. This API for their own accelerator. So actually Intel or FPGA provide this RTL code of the inside of the FPGA. This RTL code is encrypted actually, so users cannot see the inside of the contents of the RTL code. But with this RTL code, the accelerators can be implemented inside of the FPGA. And then based on this architecture, Intel and FPGA provide the API. So this API is very similar to some kinds of PyTorch or some other machine learning API framework. So with this framework, the programmers and actually the normal user can can use this accelerate hardware implemented on the FPGA board. Okay, so that's very interesting. But the learning curve is so steep. Yeah. So domain specific. I will summarize the domain specific architecture. So domain specific architecture actually the composed of a dedicated computer engine and then also dedicated on-chip memory or buffers. So actually, in order to design this domain specific architecture processor, we need the hardware design effort, and then also programmability is the main issue of the domain specific architecture. So actually, for the general purpose processor or GPU, the community or some company supports the compiler and development environment. But for this domain specific architecture for this domain specific architecture, we need a dedicated instruction set architecture, also dedicated compiler, and then actually this hardware only supports a specific domain. So the compiler or some other programming language is not supported by some program community. And then FPGA or ASIC. So we know that ASIC is performance of ASIC is better than the FPGA, but the disadvantage of the ASIC is the less programmability. So if the chip is designed with the ASIC, then we cannot modify this content of the chip. But FPGA is different. FPGA is the programmable gate array, so we can implement any hardware in the FPGA. But the main issue of the FPGA is the performance and the power consumption, and also the FPGA is expensive. Okay, so I will conclude this domain specific architecture, and then this is the last topic of this course. 도메인 스페시픽 아키텍처는 이걸로 이제 마치도록 하고요. 사실은 이게 뭐 리센트가는 사실 전통적인 이제 컴퓨터 아키텍처라고 이제 보기에는 약간 이제 뭐 좀 다를 수도 있긴 한데, 어쨌든 이제 아키텍처 필드가 지금 변해가고 있습니다. 왜요? 이것 때문에 모어스로가 계속될 수가 없어요. 우리가 좀 더 좋은 하드웨어를 만들려면은 이제는 아키텍처를 진짜 뜯어서 고쳐야 되는 그런 시대가 되어 버렸습니다. 이게 참 그래가지고 이제 많은 데이비드 패터슨 교수 같은 경우에는 뉴 골든 에이지 오브 아키텍처라고도 얘기를 하고 있고요. 그러니까 사실 도메인 스페시픽 아키텍처를 보게 되면은 이게 ASIC인지 컴퓨터 프로세서인지 약간 이제 그 중간 영역에 위치를 해 있다라고 이제 보면 되겠는데요. 어쨌든 정말 새로운 어떤 필드라고 이제 볼 수가 있겠고요. 근데 이제 문제는 뭐 이런 도메인 스페시픽 아키텍처가 이제 점점 더 우리의 이제 서버 시스템으로, 그 다음에 새로운 프로세서로 등장을 하게 될 거라는 거죠. like GPU, 그러니까 GPU처럼 GPU가 이제 처음에는 이게 뭐 우리가 이제 패러럴 프로세싱에 좋은 건 알고 있지만 뭐 그냥 게임이나 이제 그래픽스에서만 쓰였잖아요. 근데 이게 점점 발전하면서 어디에 쓰여요? 머신러닝에도 쓰이고 암호화폐에도 쓰이고 여러 가지로 쓰이고 있죠. 도메인 스페시픽 아키텍처도 아마 그런 전철을, 그러니까 그런 트렌드를 밟지 않을까 그렇게 생각을 하고 있습니다. 결국에는 우리가 GPU를 이용하려면 GPU를 이해를 해야 되고 GPU 프로그래밍 할 줄 알아야 되고 뭐 그런 거죠. 물론 이제 많은 프레임워크가 편리하게 제공을 하고 있지만 그 밑에는 큐다가 돌고 어쨌든 GPU 인스트럭션이 들어가고 그런 거죠. 도메인 스페시픽 아키텍처도 마찬가지가 되지 않을까 그렇게 예측을 하고 있습니다. 결국 거기에 맞게 어떤 머신러닝이면 머신러닝, 뭐 페이지 랭크 이런 서치 엔진이면 서치 엔진 거기에 맞도록 이제 도메인 스페시픽 아키텍처 프로세서가 개발이 되고 거기에 맞도록 그다음에 인스트럭션이 또 정비가 되고 프로그램이 그 위에서 돌고 이런 식으로 이제 되는 그런 새로운 어떤 프로세서 구조, 그 다음에 컴퓨팅 환경, 그 다음에 프로그래밍 환경 이런 곳으로 이제 나아가지 않을까 그렇게 이제 생각을 하고 있습니다. 뭐 한번 결국 모든 것이 이제 컴퓨터 위에서 돌아가기 때문에 결국 이제 컴퓨터 환경, 컴퓨터 시스템이 기존에 이제 뭐 A식이라든지 아니면 이런 부분들을 다 이제 끌고 들어오느냐 아니면은 어떻게 되느냐 뭐 알 수는 없지만 새로운 어떤 진짜 우리가 이제 과거에는 생각하지 못했던 어떤 새로운 환경의 컴퓨터 구조, 컴퓨터 시스템이 이제 된다라고 이제 보면 될 수 있겠습니다. 네. 수고 많았고요. 네. 어쨌든 이거는 이제 라스트 토픽이기 때문에 강의는 이번 학기는 이걸로 이제 마치도록 하겠습니다. 다음 주에는 이제 제가 이제 그 시험을 대체할 수 있는 이제 숙제를 이제 마련해서 이제 올릴 거고요. 한 학기 동안 어쨌든 수고 많았습니다. 계속 뭐 올라오긴 하겠지만은 어쨌든 강의는 이것으로 마치도록 하겠습니다. 좀 끝나려니까 아쉽긴 한데 어쨌든 다음 주에 다시 만나든 어쨌든 뭐 그러도록 하죠. 예, 수고 많았습니다.